Okay, so let's begin the morning session. Our first speaker is Professor Dorian Goldfeld from Columbia University, and he will be speaking on an asymptotic orthogonality relation for GLNR. Let's welcome him.
Can everybody hear me? First of all, I'd like to thank the organizers of this conference for inviting me to such a beautiful location and such a wonderful conference. So everything I will talk about today is a generalization of work of Dirichlet from the 1800s. Dirichlet, at the time of Dirichlet, a group was not invented yet, the notion of a group. But nevertheless, Dirichlet constructed for the first time a character of a cyclic group. And these are now called Dirichlet characters. And these are functions from integers to complex numbers, which are multiplicative, completely multiplicative. Chi of AB is chi of A times chi of B. A and B are integers. And they are periodic with some period Q. And chi of A is 0 if A and Q have a factor, common factor bigger than 1. So let me now present the orthogonality relation for the Dirichlet character. Assume that A and Q are integers coprime. The orthogonality relation says that if I sum, it turns out there are finitely many characters mod Q, and the number of characters mod Q is Euler's function phi of Q. So if you sum chi of n chi bar A, chi bar is the complex conjugate, you sum of all characters and divide by the number of characters, it's either 1 or 0. Dirichlet found this relation because he was trying to prove infinitely many primes in an arithmetic progression. The proof of infinitely many primes was known to the Greeks. It's very old. But at the time of Dirichlet in the 1800s, they didn't know how to prove there are infinitely many primes congruent to 2 mod 5. There was no proof at that time. So he used this orthogonality relation to prove infinitely many primes in a general arithmetic progression. Let me explain how he did it. Of course, there have been countless other applications since then. So the key idea goes back to Euler. Dirichlet introduced the Dirichlet L function. It's a sum chi of n over n to the s. Infinite sum. And since chi is completely multiplicative, it's easy to see that it has this product. This is the Euler product, so-called Euler product. Now, in analytic number theory, if you see a product, the first thing you want to do is take the log. We always do that. And so we're going to use the Taylor series for log of 1 minus x. So what he did is this doesn't work. The pointer doesn't seem to work on the screen. But he takes the log of ls chi, multiplies it by chi bar of a, and averages over chi. And then if you work it out, you see that here you have the orthogonality relation. And that sum is 0 unless p to the k is congruent to a mod q. It sifts out the primes in a progression because of the orthogonality relation. Now Dirichlet wanted to prove that So you're just left with primes in an arithmetic progression. And he wants to let S go to 1. When k is 2 or greater, the sum over 1 over p squared converges. He wants to prove that as S goes to 1, the sum on the right goes to infinity. That will prove infinitely many primes in the progression. Now, one of these characters is a trivial character. And for the trivial character, Ls chi is essentially the Riemann zeta function. And the zeta function has a pole at s equals 1. So as you let s go to 1, you'll get infinity. The problem is that we don't know that the other characters can't vanish at 1. If L1 chi was 0 for some chi, you would get minus infinity. They could cancel out. And the most difficult thing in Dirichlet's proof was to prove that L1 chi is never 0. But I don't want to say any more. But this, everything I do now is a generalization of this construction. Let me now consider this in a more modern setting. I'm going to take the group GL1 of the adels over Q, GL1 A sub Q. So A sub Q is the ring of adels. The orthogonality relation for Dirichlet characters is really the orthogonality relation for GL1 of AQ. An automorphic representation for GL1 of AQ is a one-dimensional representation. It's just the Dirichlet character, but you have to lift it to the Adel ring. Also, chi of n can be interpreted as the nth coefficient of a GL1 L function. So this is the modern way of talking about what Dirichlet did. This is the modern way. So now the question is, what if we go to higher general linear groups? Like GL2 would be the group of 2 by 2 matrices, GLN, the group of n by n matrices. Let me first say something about the history of the orthogonality relation for GL2. I will start with an orthonormal basis of cusp forms for the modular group SL2Z. A cusp form is a function of a complex variable, and if ABCD is a SL2Z matrix, it's invariant under Z goes to AZ plus B over CZ plus D. And I'm going to take an orthonormal basis. It's well known that every Moss form has a Fourier expansion in terms of the K Bessel function. And each Moss form is an eigenvalue of the Laplacian. And the eigenvalue is 1/4 plus Tj squared. The Tj is parametrizing the K Bessel function. And each such Moss form has an L function. And the coefficient Aj of n, this is the analog of chi of n. On GL1, you would have a chi of n. Here we have Aj of n. And you can compute Aj of n using Hecke operators. It's an eigenfunction of the Hecke operators. And the first orthogonality relation I could find anywhere in the literature was in 1978 in a paper by Bruggemann in Invenciones. Now, in the case of Dirichlet characters, they're only finitely many, so it's a finite sum. It turns out that there are infinitely many Moss forms. This was first proved by Selberg using the Selberg trace formula, that There are infinitely many such Moss forms. And the orthogonality relation says if you look at the mth coefficient and the nth coefficient, and you take an infinite sum and let t go to infinity, you get either 1 or 0. That's the orthogonality relation. I call it an asymptotic orthogonality relation. The next paper in the literature I found was in 1984. Sarnak essentially rediscovered Brueggemann's formula without referencing it at all. I don't think he was aware of it. And there were several important papers obtaining similar types of orthogonality relations. The first one was by Conry, Duke, and Farmer. And the second one was by Jean-Pierre Serre. Serre basically considered holomorphic modular forms. And there are finitely many. So the orthogonality relation is really a finite sum. Anyway, that's the history for GL2. Let me now talk about GLN, where n is bigger than 2. So let pi be a unitary cuspidal automorphic representation of GLN AQ with a standard L function. The coefficients of the L function are lambda sub pi of n to the minus s. The standard L function is always an eigenfunction of the Heck operators. This function was first introduced and studied by Godin and Jacquet in 1972. They proved that this function has an analytic continuation. It will be holomorphic for all values of s. It will be an entire function. And it has an Euler product and a functional equation similar to the Riemann zeta function and the Dirichlet L function. But it will have more gamma factors. The functional equation of the Dirichlet L function is 1 gamma because it's GL1. This function will have n gamma, a product of n gamma functions, because it's GLN. So we will talk, on this talk, I'm just going to focus on the simplest possible case. Unitary cuspidal automorphic representations with trivial central character which are globally unramified. This is the simplest possible case. And these can be studied in classical terms on this quotient space. GLNR, you take the quotient by SLNZ on the left and the quotient of the orthogonal group times R cross on the right. So we can study, since it's globally unramified, it will have to live on this space. So we have a generalization of the classical upper half plane. This is GLNR factored by ONR cross R cross. For example, for the classical upper half plane, it's a quotient of GL2R minus O2R, modulo O2R cross R. And it's basically matrices YX01, where X is real and Y is greater than 0. And this is isomorphic to the classical upper half plane. So H of n, for n bigger than 2, is the generalization of the upper half plane. And now we want to consider what is a Moss form, a Moss cusp form on this space. It satisfies several properties. First of all, it's a function from the generalized upper half plane to the complex numbers, complex valued. It has to be smooth. Secondly, SLNZ acts on this space by matrix multiplication. It has to be invariant phi of gamma g has to be equal to phi of g for all gamma in SL and Z. It has to have moderate polynomial growth in the y variables. And it has to be a joint eigenfunction of the ring of invariant differential operators on this space. So this is it also has to be a joint eigenfunction of the ring of Hecke operators. We can classify these Moss forms using Langlands parameters. The Langlands parameters are very simple. It's just n complex numbers that add up to 0. Very simple definition. And we can classify automorphic representations just using these parameters. So this is the theorem of Stephen Miller from 2002. Let phi be a Hecke Moss form for SLNZ with Langlands parameters alpha. Then basically this is the Laplace eigenfunction. This function has to be an eigenfunction of the Laplacian. Okay? The Laplacian on GLN. And it's basically the sum of the alpha I squareds over 2 is essentially will be the Laplace eigenvalue. And there's a conjecture, the so-called Ramanujan conjecture at infinity, that these numbers are all real. Real. That they can't be complex. It's proved for SL2Z. It's not proved for SL3Z and higher. It's still unproved. So the L functions attached to Moss custom. Let's talk about the L function. Remember that a Hecke Moss form has Hecke eigenvalues, lambda sub phi of k, when k is 1, 2, 3, 4. And you can make the L function using those Hecke eigenvalues. And it will have the Euler product. The alphas of pi that appear here are the so-called Satake parameters. It's not the same as the Langlands parameters, Satake parameters. This function will have a functional equation with n gamma factors, and the Langlands parameters will be in the gamma factors. It will live inside the gamma factors. Once we have such an L function, we can create the Rankin-Selberg L function, which is defined by an Euler product. It's conjectured that this function should be automorphic for GLN squared. That's only been proved when n equals 2. It's a theorem of Dinakar-Ramakrishna. When n equals 2, this is automorphic for GLN. There's a Langlands functoriality conjecture if you could prove Langlands functoriality, you would prove that all of these Rankin-Selberg L functions are automorphic. There's also the adjoint L function, where you take the Rankin-Selberg L function and divide it by the zeta function. All these L functions, so the Rankin-Selberg L function, from the point of view of automorphic representation, is just a tensor product of the two representations. And this involves the adjoint representation. But I'm presenting these functions, these L functions, in elementary terms, just using Euler products. Very elementary terms. So, let me now state the asymptotic orthogonality conjecture. This was first conjectured by Fan Zhu in 2014. I start with an orthonormal basis of Hecker-Maas forms, or SLNZ. Each one has these Langlands parameters. Each one has Hecker eigenvalues. Since there are infinitely many such Maas forms, I can't, in the orthogonality relation, I can't just take an infinite sum. I have to put a weight function in there to make everything converge. So I take h sub t is just a smooth weighting function to make things converge. But the support is on the eigenvalues that are less than t. The support of this function is for those eigenvalues. And I also remind you of the adjoint L function, which appears in the orthogonality relation. So let L and M be positive integers. Then for some theta greater than 0 and capital T going to infinity, this is the orthogonality. This is the conjectured orthogonality relation. So these are like the Lth and the mth coefficient of the L function. H is a function that has support on the interval 0 to t's. And we get an asymptotic orthogonality relation. It's either 1 plus something very small or something very small. If L equals M, it's basically asymptotic to 1. Otherwise, it's 0. So this was first conjectured in 2014. So let me now tell you what has been done since then in trying to prove this kind of a conjecture. So let me start with GL3. So this is a theorem I proved with Alex Kantorovich in 2012. We basically proved the conjecture of Fanju for GL3. We proved this theorem with a very explicit error term, t to the minus 2 plus epsilon. And even the dependence on M and L is given explicitly. Valentine Bloma, in the same year and the same time, proved the same result, but with a completely different method. And then more recently, Blomer, Butkain, Ralph obtained further results in this direction. This is all more than 10 years ago. Now let me tell you about what happened after. So these are now more recent results. So in 2021, Eric Stade and Mike Woodbury and I basically proved Fanju's conjecture for SL4Z for the first time. And shortly, again in the same year, Motz, Templier, and Finis-Motz, in a major breakthrough, proved an asymptotic orthogonality relation for all SLNZ. We just did it at that time for SL4. But without the harmonic weights, the adjoint L function values, without those values, it was a different formula. And the power savings error term they obtained was much weaker than the ones we obtained on. Even for SL4Z, they had a much weaker result. But this was this was really a major breakthrough. But they used the Arthur-Selberg trace formula, whereas we were using the Kuznetsov trace formula. That was the difference. So now I want to discuss what's the difference between the Arthur-Selberg trace formula and the Kuznetsov trace formula. What makes it different from the point of view of asymptotic orthogonality? I'm going to compare these two trace formulas. So in the Arthur-Selberg trace formula, there are no harmonic weights. For applications to L functions involving period formulae, it's often desirable to have this additional factor, 1 over L1 adjoint phi. L sub j to the minus 1 is equal to this. It's the 1 over the adjoint L function. The other key difference is in the Kuznetsov trace formula, there's no residual spectrum at all. It doesn't appear. So you get, just from that, you get a very strong power savings. If you use the Selberg trace formula, there will be residual spectrum. And it's very hard to get a good estimate. So it makes the error terms much, much bigger. So that's what I said in the last point here, that the spectral side contains, in the Arthur-Selberg trace formula, residual spectrum. Now let me just go back to the conjecture. You see when we prove the orthogonality conjecture, there's a 1 over Lj. Lj is the adjoint L function. It's there. If you use the Arthur-Selberg trace formula, you don't have that. It's not there, but you get much worse error terms. So let me now talk about the vertical Sato-Tate problem. So the Sato-Tate problem is a very famous problem. You take an elliptic curve, and then there's this Sato-Tate measure, and you want to prove what it is. Basically, what you're doing is you're fixing an elliptic curve, counting for each prime how many points on the curve. And you want to know what happens as you average over primes. In vertical Sato-Tate, you do the opposite. You pick a prime, and then you vary the elliptic curves, and you want to know what happens on average. So the vertical Sato-Tate problem was first solved for elliptic curves by Serre, by Jean-Pierre Serre. Yeah, and Bruggemann, Sarnak, Serre, all these people studied this problem. But it turns out that the lambda j of p, as j varies, is equidistributed with respect to the Plancherel measure, which depends on p. Fanju showed that if we give lambda j and p the harmonic weight, lambda j inverse, 1 over the adjoint L function, then you get exactly this Sato-Tate measure, not the Plancherel measure. So for the vertical Sato-Tate problem, you have to use the Kuznetsov trace formula because the adjoint L function appears there naturally. And in a recent paper, Jaina and Mata Shanalan just a few years ago generalized Jou's results by proving an asymptotic orthogonality relation with harmonic weights using the Kuznetsov trace formula. But he doesn't obtain a good power savings. He doesn't obtain power savings error. He has a weak error term. Yes. Classical is horizontal, and this is vertical. Yeah. So now I'm going to state the main theorem of this talk. This is the new theorem that we recently proved. We start with a test function. which will be a Gaussian times a fixed polynomial, which has support on eigenvalues less than t. And this is the theorem we just recently proved. We have to assume two conjectures, the Stade conjecture and this lower bound conjecture. I'm going to explain what those conjectures are in a few minutes. But let's just, so the Stade conjecture we can prove up to SL7 actually. Then we have this, we prove this, this formula. And you'll notice that we have n-1 secondary terms in the asymptotic formula. It's a very accurate formula, and the error term is very strong. In the work of Templier and Mott, they only have the main term. They don't have the lower order terms. So this is the main theorem of this talk. Any questions? So in the last 15 minutes, I will give some ideas of how we prove this. So first of all, Stade conjecture is proved up to GL5, but we can actually went to GL7. The lower bound conjecture is proved for n equals 4. Yes, I'm going to explain it. It's very related. And the lower bound conjecture is proved for n equals 5 by Kim Shahidi in a paper in 2002. So this theorem is unconditionally proved up to GL5. But for GL6 and higher, we need these conjectures. So now I want to talk about these conjectures. So I have to define a character of the unipotent group. This is the unipotent group. There's ones on the diagonal, zeros below, arbitrary real numbers above. So a character is just, you use the superdiagonal. E to the 2 pi I, k1 u1 2 plus k2. That will be a character of the group. The ki are integers. And then clearly this is a multiplicative character. And I need to define the Whittaker function. So we start with Langland's parameters. So the sum of the alpha I is 0. And let psi be a character of the unipotent group. A Whittaker function is a smooth function satisfying from the generalized upper half plane to the complex numbers, satisfying the following properties. First of all, it's an entire function of the alphas of the Langland's parameters for every g in the generalized upper half plane. First of all, when you multiply G by a unipotent matrix on the left, this U shouldn't be here. There's a typo. You just get chi of U times psi n alpha of G. Also, it should be an eigenfunction of all the invariant differential operators. And it should have these growth conditions. What? You mean this? Yeah, there's something wrong there. Oh no, this is W, sorry. W is equal to psi of U, and then W and alpha G. Yeah, there shouldn't be a G there, a U there. Okay, I now want to define Jacquet's Whittaker function. Jacquet, in his thesis, showed how to construct the Whittaker function as an integral. So I have to define the power function. So we start with Langland's parameters. This rho is just very special rational numbers. And we define the power function, absolute G of alpha plus rho, to be this product. So on the upper half plane, the power function is y to the s. This is a generalization of y to the s. And we construct Eisenstein series by averaging the power function over the group. This is the generalization. But instead of s, we have the Langland's parameter. And this is Jacquet's Whittaker function. I write it in this form as using a product of gammas. So it has a functional equation, and the functional equation is you can just permute the Langland's parameters any way you want and nothing changes. That's the functional equation. And you basically, you integrate the character, the power function against the character. That was the idea. You take the power function times the character and you integrate it over the unipotent group. All right, let me now say, we have these two conjectures, Stade and the other one. The Stade conjecture says that if you take the Mellin transform of the Whittaker function, not the Whittaker function, but its Mellin transform in S, in a complex variable S, then it should be some linear combination of shifted Mellin transforms where you have these shifts by sigma. Basically, it's a generalization of the gamma function. See, the gamma function satisfies this identity. Gamma of S plus 1 is S gamma S. It's basically a generalization of the gamma function. So let me just give you two examples. I'm going fast here because I'm running out of time. In the case of SL2Z, the Mellin transform of the Whittaker function is a product of two gammas. So it satisfies these gamma relations. So the Stade conjecture is easy to prove. In the case of SL3Z, the Mellin transform of Jacquet's Whittaker function is a product of 6 gammas divided by 1. You see that the Langland's parameters appear inside. Since the gamma function has this transformation property, you can easily prove the Stade conjecture. When n is greater than 3, the Mellin transform is not a product of gammas. So it gets very hard to prove anything. E to the minus u. If you integrate from 0 to infinity, e to the minus u against y to the s, dy over y, you get gamma by definition. All right, now I want to talk about the other conjecture that we need. This is the lower bound conjecture. So I have to define the Iwaniak-Sarnak analytic conductor. Let phi be a Hecker-Moss form for SLNZ with Langland's parameters alpha. The analytic conductor is just basically the product of the absolute values of the alphas. Remember that if you have a Moss form, it's an eigenvalue of the Laplacian. And the eigenvalue is the sum of the squares of the alpha i's in absolute value, essentially. So this will be the analytic conductor. Now I can state the lower bound conjecture. I create the Rankin-Selberg L function. And I want a lower bound for this L function at 1 plus it. And the conjecture says that you get this kind of a lower bound. So this is proved for if phi and phi prime are on GL2, this is known. It also follows from the Riemann hypothesis. If we knew the Riemann hypothesis for Rankin-Selberg, you could easily prove it. But it also follows from Langland's functoriality. If you had Langland's functoriality, you would know that the tensor product of phi and phi prime is automorphic for SLn times n prime z. And then using the method of de la Vallée-Poussin from 1904, Sarnak showed you can get this lower bound. But you need to know that that phi cross phi prime is automorphic. So you have to prove modularity for these tensor product representations. What's known about this type of Langland's functoriality? In the case of n equals n prime equals 2, Dinakar Ramakrishnan proved that it's modular for SL4. And more recently, when n equals 2 and n prime equals 3, Kim and Shahidi in the Annals of Math proved modularity. These are remarkable results. They allow us to unconditionally prove very strong asymptotic orthogonality relations for SL4Z and SL5Z. Unfortunately, no one knows how to prove modularity beyond GL5. So this is the lower bound conjecture. I call it LBC. Chao Zhang in 2022 proved this kind of a lower bound. This is the strongest lower bound known. Unfortunately, it's not enough to allow us to prove the orthogonality. It just misses by a factor of 1/2. And this improves on a result of Brumley of 2006. If one could prove this bound where the theta is less than 8 over n squared, then we could prove everything we want. So we don't need Langland's functoriality. We don't need that. If someone is very strong in analytic number theory, there's a chance there's a chance to prove this. It's very close, just a little bit more. So in fact, this establishes a black box by which improvements to bounds on Rankin-Selberg L functions. You just need lower bounds on Rankin-Selberg L functions. If you could just improve the power savings a little bit, then we could get very strong results. So now, some ideas in the proof of the theorem. I need to introduce Langland's Eisenstein series. So I will give a very simple definition. So I have to define the parabolic. This is the standard parabolic subgroup. Zeros below the diagonal and arbitrary things above the diagonal. N1 plus N2 plus NR adds up to N. And then we have the unipotent radical. And then we have the Levy subgroup. You have these three groups. I have to define an automorphic form associated to such a parabolic. So we start with a partition of N, and we have this parabolic subgroup. For each Ni, I have a Moss form, phi I, for GL Ni sub R. And then this automorphic form, I can create a global automorphic form, capital Phi, induced from the Levy subgroup, so, which is defined as follows. It's just a product of the phi I of Mi. So given a parabolic subgroup, I can define a cusp form on this parabolic subgroup by this product. And as you see on the bottom, this phi satisfies phi of UMK is phi of M. For all unipotent matrices, for all M in the Levy, and for all K in the orthogonal. And now I want to define a power function. So for GL2, you have x plus iy. That's the upper half plane. The power function is y to the s. On GLN, well, when you're working with matrices, instead of x plus iy, you have x, y, 0, 1. And on GLN, you have a matrix with ones on the diagonals and x's on the right, and then a diagonal matrix with y's. Yeah. So the power function will be the determinant of the MI. So it's basically products of powers of y. So to construct a Langlands-Eisenstein series, we first have the group SLNZ. We have a parabolic subgroup. We have such a Moss form on the parabolic subgroup. We have complex variables. And we have this power function like y to the s. That's the Eisenstein series. You average over the group the power function times the automorphic form. And I think I have maybe one or two more slides. Can I go over a few more minutes? Yeah. So now we consider the Hilbert space, h to the n mod SLNZ. We define this inner product on the space. And we have the Langlands spectral decomposition. This is the big theorem of Langlands, that any automorphic function on SLNZ, automorphic for SLNZ, has a spectral decomposition. It's first an infinite sum over Moss forms. You take the inner product of F with the Moss form, and then you take this thing on the bottom is going to be the adjoint L function. And for the Eisenstein series, it's the same thing, but you have an integral. Instead of a sum, you have an integral of Eisenstein series. So if you choose the right kind of function, you can construct things so that this sum is exactly the orthogonality relation. But the right choice of F. This is exactly the orthogonality relation. And then the problem is you have to we don't know what this stuff is, but we have to bound it. and the error term will depend on the bounds for these Eisenstein series. Now for the Eisenstein series, we know the Fourier coefficients of the Eisenstein series, but we don't know the first coefficient. But this is my last slide, but we proved this formula for the first coefficient recently. These are all the ingredients. Then the first coefficient is given by a product of adjoint L functions and a product of Rankin-Selberg L functions. But the Rankin-Selberg L functions are to the -1 power. So we need a lower bound for these L functions. That's the lower bound conjecture. If we have a good lower bound for these L functions, then we can do what we want. So I will stop here. Thank you very much for listening.
Okay, thank you. Are there any questions? The lower bound for the Rankin-Selberg. Yeah. The only way I know how to prove that is by functoriality. At the moment, nobody knows how to do it. I mean, we can prove these kinds of things in the function field case, but not for number field. Modularity, it just means that something is automorphic. In other words, phi of az plus b over cz plus d is phi of z classically. Right? It's a modular function. It satisfies modular. And modularity is for holomorphic functions. Automorphic is the same thing, but the functions don't have to be holomorphic. Any other questions?
Yes, that's because we use Poincare series, which are orthogonal to residual spectrum. I didn't explain that. Yeah, we take the inner product of two Poincare series, and both of them are orthogonal to all residual spectrum. That's how the Kuznetsov trace formula works. But I didn't want to get into that. I would need another half hour to explain that.
How to choose the test function f in last page?
Which function? Back? How many pages? Yeah, that f will be basically a product of two Poincare series. I mean, if you look at Kuznetsov original paper, he used Poincare series. The Poincare series is constructed like the Eisenstein series, except for the Eisenstein series, you take a power function and average it. For the Poincare series, you take a power function times a character and average it. That gives you Poincare series. And you can show that the Poincare series is orthogonal to the residual spectrum. Our paper is online. You can find it easily so you can see.
Any more questions? So if not, let's thank the speaker again. And the next talk will be at 10:30.